Everyone, our lesson for today is about the three-dimensional kinematics of a rigid body. Part 1. Rotation about a fixed point. The angular position, the Greek alphabet theta, it is the angle between our reference point and our current position. The angular velocity, it is given by the change of theta, our angular position, over the change of time. Angular acceleration, given by the Greek letter alpha, it is the change of angular velocity over time. We also have this equation which relates the angular velocity to the angular acceleration if time is eliminated. This is our equation for the constant angular acceleration. Notice that our equation for the constant angular acceleration is similar to the equation we use for linear acceleration. Magnitude of velocity. Angular velocity is not equal to the linear velocity. The magnitude of velocity we're using, it is given by the angular velocity times the distance between the center, the fixed point, to point A. So it is V equals to the angular velocity times R, which is the distance between the center, the fixed point, to point A. Tangential and normal acceleration at point. So this is our equations for tangential and normal acceleration at point A. We have the scalar and the vector acceleration. Our acceleration is given by the sum of our tangential and normal acceleration. We can also use this equation. So rads to revolution. If rads to revolution conversion, 1 revolution is equal to 2 pi rad. And degree to radian conversion, we will multiply the degree to pi over 180. And for radian to degree, we will multiply the radian by 180 over pi. Here's our problem. The pinion gear A on the motor shaft is given a constant angular acceleration of 3 radians per second. If the gears A and B have the dimensions shown, determine the angular velocity and the angular displacement of the output shaft C when the time is equal to 2 seconds starting from rest. The shaft is fixed to B and turns with it. The radius for our gear A is 35 centimeters and B is 125 centimeters. So we will use the constant angular acceleration equation that we were given. So the angular acceleration equals to the initial angular acceleration plus our angular velocity is equal to the initial angular velocity plus angular acceleration times time. So our angular velocity is equal to 6 radians per second. We will also get this answer if we use this other formula, which gives us our theta equals to our angular position equals to initial angular position plus initial angular velocity times time plus 1/2 times angular acceleration times time. So we will still get the same answer, which is 6 radians. So we will use this. We will plug in the answers we have. So angular acceleration A times radius of gear A equals to angular velocity B times the radius of gear A equals to angular velocity B times radius of gear B. So 6 radians for our angular velocity of A times 35 equals to angular velocity of B times 125 for the radius of our gear B. So our answer here is the angular velocity of B is 1.68 radians per second. So because the shaft is fixed to B and turns with it, so we have the same for this is the angular velocity for our gear C, which is 1.68 radians per second.